So in the previous lecture, we had seen the two ways to represent a graph. Okay, so both the methods we had discussed, adjacency matrix and adjacency list. So today we are going to cover how we are going to do traversal in a graph. If you remember, we had also learned how to do traversals in a tree. Okay, so we had learned that there were three types of traversals. Common traversals were in order, pre-order and post-order. So in this slide here, we are just looking at some of the differences in the traversal between a tree and a graph. So in a tree, if you remember, we always started the traversal from some root node. Okay, but in a graph, we do not have a root node. So the traversal can start from any vertex. Okay, please remember this. It can start from any vertex. So you can take any vertex in the graph as the starting vertex. Depending on what you take as a starting vertex, the same algorithm will produce different answer for different vertices. So you'll get a different sequence for each vertex. So if you take, so some students, if you suppose, for example, there are three nodes in the three vertices in the graph A, B and C. So if some students take A as the starting vertex, they'll get some particular sequence. Other students who take C as the starting will get some sequence and so on. So the answer may need not be the same at the end. Okay. Then also in a tree, we are guaranteed to visit all the vertices or all the nodes. Okay. But in a graph, we may not be able to visit all the vertices. We may be able to visit the vertices only which are reachable from the starting vertex. Okay, so some nodes which are not connected or some vertices which are not connected may not be reachable at all. So it may not be possible to cover all the vertices in that traversal. So for example, you are having a graph like this. Okay, and say there's one node like this D. So if we start from here, okay, the vertices that are reachable from here are this A. From A you can go to B and you can go to C, but you cannot go to D. So in the answer you may get these three vertices as the sequence, but you will never get this. Okay, so that is also a valid answer in case you are not able to reach some vertices, but that is also a valid answer. So in a tree, while traversing, we never encounter the vertex more than once. Okay, but in a graph, we can encounter that same vertex more than once. Okay, because like we learned, in a graph we can have cycles. Because there are cycles, there is more than one path to reach. Okay, so that each vertex can be reached more than once. But in a tree, there are no cycles. So each vertex is visited only once. Okay. Then, like we have already discussed, in a tree we have unique traversals. Okay. Only one sequence of vertices. Suppose we are doing an in-order traversal or pre-order, post-order. You will always start from the root node and then you will get the same answer. Every time you apply that traversal, you will get the same answer. You will not get different answer. But in a graph, suppose you learn a method and you apply it, depending on from where you start in the graph, from which vertex, you will get different sequences. Okay. So there are two main methods of traversal in a graph: breadth first search or BFS and depth first search or DFS. So BFS and DFS. Okay, so we are going to learn both these methods today. So the first method is this breadth first search. So you can refer to this PDF which has been shared with you. You can refer to this algorithm as I'm going to solve it. Okay, so these are the steps that we are going to do. I'll show you with the help of an example all the steps. Pretty simple. Okay, breadth first search is implemented using a queue. Okay, we use a queue data structure like we have already studied. Queue is a first in first out data structure. Okay, so just to revise, you had a queue like this. Then there were two pointers. One was a front pointer, one was the rear pointer. Insertions would take place at the rear, insertions, and deletions would take place at the front. Okay, and whichever element came in first was the first element out. This was your queue data structure. So we are using this queue data structure while implementing breadth first search. Okay, so when we are implementing this algorithm, the vertex will be in one of the tree states: initial, waiting, or visited. Initial means initially when before you start with the algorithm, all the vertices will be in the initial state. Okay, you can note down what I'm saying. It's also there here in the slide. At the start of the algorithm, all the vertices are in the initial state. When a vertex is inserted in the queue, its state will change from initial to waiting. So if a vertex is inserted in the queue, its state will be waiting. When you delete a vertex from the queue, we will call that vertex as visited. Okay, and you will change the state from waiting to visited. So basically, we are going to do these steps. Okay, so we're going to apply it, say, to this graph. Okay, so you'll get a question in the exam for around 8 marks. Okay, which will tell you traverse the following graph using breadth first search. They will not mention that you have to use queue or something like that, but you have to use queue to solve it. Okay, they may mention or they may not mention that you have to use queues, but you have to solve it using queues. So you have to decide, like we have discussed before, you out of this so many vertices that you can see here, 9 vertices, I could have selected any vertex as my starting vertex. Okay, but just so that we get a common answer, we will always take, suppose numbers are given, we'll take the lowest number as a starting vertex. Okay, or if alphabets are given, suppose these were alphabets, then we would have tried to start from where A was there, or any appropriate lowest letter or the first letter when you go alphabetical order. Okay, so it's always better to start like that, so that you can compare your answer with others. So for exams or for ITs, if you get something like this, please start with the smallest number in case numbers are given, or in alphabetical order, suppose alphabets are given. Okay, so in this case, while applying breadth first search to this graph, we're going to start from 0. Okay, now just to make things easier for you, we say initially queue is empty. Okay, and all the vertices are in the initial state. Now to show you the vertices in initial state, at the beginning what I'll do is, on this slide I'll just circle all these vertices with a different color to tell that these vertices are in a initial state. Okay, just to tell you that these vertices are initial state, I will circle them with red. So this, let's assume that since they are in red, they are in the initial state. Okay, then we have to perform the steps one by one. So we go to the first step. We take the starting vertex and insert it into the queue. Like we have said, whenever the vertex is in the queue, then its state will be waiting. Okay, so we take, first you have to select your starting vertex, so you have to mention it. So we will say that we are taking vertex 0 as the initial vertex. Okay. Then we insert. Then while solving, you are going to have 4 columns. Okay. So one column will be telling what operation you are going to perform. Second column will be keeping track of your traversal, breadth first search traversal. Third column will be keeping track of the adjacent vertices. Okay. And the fourth will be your queue. So when we had studied queues, we had shown it in the form of an array like this. Shown it in the form of an array. Okay. Now if you see in this slide here, we're not going to show it in the form of an array, but it's understood. Okay. It's understood. And those pointers are also not going to be shown to you front and rear, but it is understood that this is a queue, and the first element will be pointed by front, and the last element will be pointed by rear. Okay, that you have to understand. So we start with our first step in the algorithm. We insert the starting vertex into the queue and change its state to waiting. Okay. Now for waiting, I will not change the color of anything here because I don't have different color here. Okay. So I insert it into the queue. So I put 0 here. Okay. Next step, delete the front element from the queue and visit it. Okay. So as long as this 0 was in the queue, its state is waiting. When I delete it, I will also visit it. And whenever I visit a vertex, I will also insert that vertex in my traversal. Okay. Just like if you remember when we were doing the traversals for a tree, whenever we used to visit a node, okay, we used to also put it in the output. So here also it means the same thing. Whenever we delete a vertex, we are going to visit it. So when we visit it, we are going to put it in the output. And this column that keeps track of the output is your traversal column. Okay. And after deleting, we are going to call that vertex. We are going to change the state of the vertex as visited. So this is what we will do now in the next slide. So I delete that vertex. Okay, I delete the vertex at the front of the queue, that is 0, and I visit it. Since I visit it, I put it in the output. Okay, since I visit it, I put it in the output. Here, visited means put it in the output. After that, you change the state of that vertex to visited. In order to show that I visited this vertex, I'll just remove this. Okay, that means 0 has already been visited. Okay, there's no red circle around it, means 0 has been already been visited. Okay, next step, look for the adjacent vertices of the deleted element. Okay, so look at the adjacent vertices. Which are they? Look at which vertices are reachable from 0. So from 0, this is your deleted vertex. So the vertices reachable from 0 are 1, 3 and 4. Okay, 1, 3 and 4. All these are reachable from 0. Okay, so we write it in this order here, in ascending order. Okay, so I write all the adjacent vertices in this column here, adjacent vertices to deleted vertex. That step is not over. Okay, continue here, and from those adjacent vertices, insert those vertices into the queue which are in the initial state. So first, this third step is having 2 parts. Look for adjacent vertices of the deleted element. So we have done it here. Okay, then insert those vertices into the queue which are in the initial state. So from among these adjacent vertices, these are your adjacent vertices now. From these, you can insert in the queue only if they are in the initial state. Okay. So check 1. Is it in initial state? Yes. So put it in the queue. Check the next one. 3. Is it in initial state? Yes. Put it in the queue. Check 4. Is it in initial state? Yes. Put it in the queue. Okay. Are you getting it? Just let me know in the chat if this is fine. You're getting it. Till here, is it okay with everyone? Okay. So let's continue. So now this is your front. Okay. 1 is at the front of the queue and 4 is at the rear. So if, like I told you, we always delete at the front in a queue. So 1 is your front and 4 is the rear. So once we have done that, once we have done the third step, step 4 tells us repeat the step 2 and 3 until the queue is empty. So you have to keep repeating these steps until the queue is empty. Okay. So we will start from here again. Delete the front element from the queue and you all can refer this from the next slide. So you all can refer this PDF has already been given to you. You can keep this algorithm open and refer it. Okay. So what we are going to do is now I'm going to keep repeating these 2 steps from here. Step 2 and step 3 until the queue is empty. Okay. So first what I do is I delete the first element, this one, 1. Okay, I delete it and I visit. What's the meaning of visit? Visit means you put this in the traversal. Okay, so I put it here. 0 was already there, so I put 1 also. Okay, I put it in the traversal. After that, I have to visit the neighbors of 1 or the adjacent vertices of 1. Which are the adjacent vertices of 1? Adjacent vertices of 1 is 2 and 4. 2 and 4. Okay, I have written them here, 2 and 4. I can insert these adjacent vertices if they are in the initial state. So I can insert them in the queue if they are in the initial state. So I check 2 and 4, both are in the initial state, so I can insert them. Okay. So there's no fixed order in which you may put them. So you could have put 2 for first and 4 later, or you could, in your textbook they have done like this. So I've just taken this option from your textbook. So any one of these 2 vertices you could have put inside the queue first. Okay. So this is the way we are inserting. So we have put both these vertices since they are in the initial state inside the queue. Now 1 has already been deleted. Okay, here we have deleted 1. So what is left in your queue? 3 and 4. Okay, 3 and 4. Now out of your 4, okay, in the previous okay, one second. Okay, so presently you have deleted 0. Okay, these three vertices, okay, were in the waiting state. Why they are in the waiting state? Because they are in the queue. Okay, like we have said here, these three vertices, whenever a vertex is present in the queue, whenever a vertex is present in the queue, its state will be waiting. Okay, so these three vertices are in the waiting state. All the other vertices are in the initial state. Okay, then we followed the algorithm. We deleted this one. Okay, here, since we deleted it, we visit one and put it in the traversal. After we put it in the traversal, next step is what? Find out the adjacent vertices. We found out the adjacent vertices. Okay, now we check if these adjacent vertices are in the initial state. Now there are two adjacent vertices of 1, 2 and 4. You can see here, I can put only the adjacent vertices into the queue which are in the initial state. Okay, so among both these vertices, only one vertex is in the initial state, that is 2. Only 2 will be inserted and 4 will not be inserted again. That's why here I have put a remark for you that 4 will not be inserted again. Okay, why? Because 4 is already in the waiting state. It is not in the initial state anymore. Okay, and adjacent vertices you can push into the queue only if they are in the initial state. So right now we are having only 2 in the initial state, so only 2 is inserted here. Clear? Okay, so I put 2 inside the queue and I change this state. I change this state from initial to waiting. Next, you have to continue doing these steps. So you have done this third step. Now you will, you have done this third step. So you will do the second step now. You repeat the steps 2 and 3 until the queue is empty. So now which vertex are you going to delete? Can you tell me in the chat? These are your options. Okay, don't look at the remaining. These are your options. So which vertex you're going to delete? Can you write the answer in the chat? Which is the front? The first element at the front will be deleted. So which is the element at the front? Yes, correct. Yes. So you will delete it. After deleting it, what is the next step? What is the next step after deleting it? Carson, once you delete a vertex, what's the next step? Please write down what I'm telling you all. Okay, it become easier for you all. So once you delete a vertex, what are you going to do? You are going to put that vertex, means you are going to visit it. So when you say visit, you're going to write this vertex in the traversal. So now you will have in your traversal 0, 1 and 3. Okay. So once you have deleted, you visit it. What's the meaning of visit? You will put it in the traversal column, and also you are going to find out the adjacent vertices of this. Okay, so I'll just write down here, this was in waiting, this was in initial state, this was in so adjacent means which are reachable from it. Where are the arrows from tree going? Okay, so where are the arrows going from tree? They are going to this vertex 4 and to vertex 6. Okay, so we have written here vertex 4 and vertex 6. These are the two vertices which are reachable from tree. Okay, now among these adjacent vertices which are in the initial state, only those vertices you can put in the queue. Out of 4 and 6 which are in initial state, only 6 is in the initial state. Okay, so therefore we have written here one remark: don't insert 4 again into the queue. So out of these two vertices, only six is put into the queue. Okay, since tree was deleted, we are having now in the queue 4, 2 and 6. Okay, so you have to continue like this. Next step, you will delete again the first element, that is 4. So once you delete that element, visit it. So visit 4 means you will put 4 in the output in the traversal column, and next step is to find the adjacent vertices of next to 4. Which are the adjacent vertices next to 4? Adjacent vertices next to 4 are 5 and 7. Okay, arrows reachable from 4 are 5 and 7. So write them here. You can insert these vertices in the queue only if they are in the initial state. Are they in the initial state? Yes, both of them are in the initial state. Okay, change their state to waiting. So you change the state of this vertex. Whichever elements you put in the queue, those elements will be changed, their state will be waiting. Okay, so now you're going to have 4 elements in the queue at the end of this step. Then again you will delete the first element, so you're going to delete 2. Once you delete, put this 2 in the answer here and visit. Okay, whenever you say visit, so we have done so many steps here. Whenever you say visit, you can remove this. Okay, so we have already seen 0. You have removed the, don't keep any marking on it. From 1 you can remove whatever you have deleted and visited, you can just remove this. Okay, to show, just to help you to show that you have already visited them. So if I just look at these vertices, I know that I have visited them. Okay, 2 also you have visited, so you can remove this. So all the other 4 vertices, if you look, you have not yet visited them. Okay, you can interpret like that. So next step that you are going to do is find the adjacent vertices next to 2. Okay, so next to 2 there is only one adjacent vertex, that is 5. Tell me whether 5 can be inserted into the queue. Can 5 be inserted into the queue? Can 5 be inserted into the queue? No. Yeah, Vibhuti, you are correct. Okay, 5 cannot be inserted into the queue because it has already been visited. Okay, like here in the previous, here we have said we have to only insert the elements which are in the initial state. Okay, so we cannot insert 5 again. Okay, so presently this is what is your diagram looking like. 8 is in the initial state, 5, 6 and 7 are in the waiting state, and these others have been already been visited. Okay, So I cannot insert 5 again because it has already been visited. It's already present. Okay. In simpler words, you can think like this, like how Vibhuti has answered. If that element is already present in the queue, do not insert it again. Okay. So you can see in each of the steps, if the element is already present in the queue, we do not insert it again. Okay. Next step, delete 6, okay, and visit. Since you are deleting 6, write it in the answer. Find the adjacent vertices. Okay, adjacent vertices of 6 are, you can see, 4 and 7. Only two adjacent vertices, 4 and 7. Okay, now next step, you have to read this. Okay, read this. So what you're going to do, insert only those vertices into the queue which are in the initial state. When you check here, check whether 4 and 7 are in the initial state. If they are in the initial state, they'll have one circle like this. Are they having any circle? Are they having? No. So you cannot insert both of them. Okay, you cannot insert both of them. They are not in the initial state. Clear? Okay, then continuing. So 6 has been deleted, so now only two vertices are left, 5 and 7. Delete 5 and visit. So when you delete, you put 5 in the traversal, okay, and you find out the adjacent vertices of 5. There is no arrow which goes from 5 to any other vertex, therefore there are no adjacent vertices. After deleting 5, only 7 remains. Okay, so you delete 7 and visit, so you write 7 in the answer. Adjacent vertices to 7 are 5 and 8. So you will write here 5 and 8. You can insert only those vertices which are in initial state. So when you look at 5 and 8, only 8 is having this circle. So like I told you at the beginning, circle means initial state. So you can put 8 inside the queue, but you cannot put 5. Okay. So only 8 will be inserted. Then in the last step, you are going to delete 8 and visit. So when you delete 8 and visit, 8 will be put in the traversal. There are no adjacent vertices for 8. There are no adjacent vertices for 8, and your queue is empty. So you can only continue until the queue was empty. Once the queue has become empty, this is your breadth first search traversal. So your answer you have to write, this final answer will be your breadth first search traversal. Okay, are you getting it? You get it, students? Got it? Aman, Aniket, Anthony, Anushka, Athena. Okay, just I'll ask you some questions. Okay, just let me know quickly because we have to learn one more method. Okay, so just looking at this diagram, you can just tell me. Okay, Avishka, from which vertex do we start in BFS? Avishka, can you hear me? You can type out your answers. Sahil Khan, from which vertex are we starting with our BFS? Okay, you don't want to answer. Should I go to the next method? Yes, students. You don't want to revise this? Yeah, I want some answer. Yeah, you start from the smallest value. Okay, we can start from the smallest value. Okay, but in reality, which is according to the algorithm, you could have started from anywhere, but we'll start from the smallest value. Okay, according to your textbook. Okay, then uh, so once we start from that, what's the first step? You take that value and insert it in the queue. Okay. Once you insert it, after deleting, what's the meaning of this visit? What do you mean by visit? When we say visit, what do you do with that vertex? Okay, students, did you all get the method? No, 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 no. That's not. Yeah. Okay. See what I'll do. I think y'all are not still understood this. What y'all do is sit with a book and pen and just write it down quickly. Okay. Y'all are not not followed it. I think. Okay. Please take your book and pen and sit. Draw this diagram. Draw this diagram, and I just explain the first 2 3 steps of this algorithm before I go to the next one. Okay. Then you can proceed. Just take your book and pen and sit down and please write it down what is being told. Don't just watch this video. You are supposed to practice what is being told. So just sit with your books and we'll do this first 2 3 steps before I go to the next method. Are you ready with your books? Just answer someone. Are you ready with your books? Okay. So let's start. Okay. I want everyone to understand this is an easy 8 marks question for you in the exams. I want everyone to get it. Okay. So you start with this, start with the algorithm. Okay. There are just 2 things that you need to keep doing it over and over again. There's the second and the third step. Okay. So first, initially, what you do is just circle all these things. Okay. If you are not having a circle, you can try keep some other mark. Okay. You can put a tick mark or something like that. Okay. So what's the meaning of this circle? Circle means all these are in the initial state. Okay. Please remember, circle means all the vertices are in the initial state. Okay. W means all the vertices will be in the waiting state. Okay. Waiting state means they are already in the queue. Okay. Waiting state means they are already in the queue. And if they are visited, then nothing will be there. Okay. Nothing will be there if they are visited. Okay. So first we start with vertex 0. I take vertex 0 and I insert it into the queue. Since it is already in the queue, I change the state. I change the state to waiting. Okay. It's in the queue. Here it's in the queue. Okay. Next step, I delete 0. I delete 0 and visit. So when I visit this means I put this in the answer. Okay. So once I put it in the answer, next step, I find out all the adjacent vertices. Adjacent means the neighbors of 0, which are reachable from 0 directly. Which are reachable from 0 directly? There are 3 vertices which are reachable directly: 1, 3 and 4. So I write down here 1, 3 and 4. Okay. Now, after I found the adjacent vertices, next I have to decide whether this will go inside the queue. Okay, since I deleted this 0, nothing is there in the queue right now. Okay, so I have to now decide whether these 3 vertices will go in the queue. They can go in the queue only if they are in the initial state. Okay, these adjacent vertices can go in the queue only if they are in the initial state. So if they are in the initial state, then I told you they'll have this red circle. Okay, so now check these 3 vertices 1, 3 and 4. Are they having a red circle? Yes, 1, 3 and 4 are having a red circle. That means they are in the initial state. That means I put them here in the queue. Okay, so once I put them in the queue, I change their state to waiting. So these 3 vertices, I put them in the queue. Which one? 1, 3 and 4. So I change their state to waiting. So 1, 3 and 4 state is changed to waiting. Why? Because they are in the queue. I told you when they are in the queue means their state is waiting. They are no longer initial state. Okay. Then you delete this first element 1. So you deleted 1. Visit. Visit means you will put 1 in the output. Okay, 1 is in the output. After you put in the output, find out the neighbors of 1, adjacent vertices of 1, who you can reach from 1. You can reach 2 vertices from 1. These are the 2 vertices, 2 and 4. 2 and 4. Write them here. Now you have to decide which of these 2 vertices go into the queue. Okay, so if they are going into the queue, you are going to insert them into the queue. What it should be? What is the condition? They should be in which state? If you are going to put them in the queue, they should be in initial state. Okay, so if you are going to put them into the queue, they should be in initial state. It is mentioned here. Insert only those vertices which are in the initial state. Okay, so among these 2 vertices, check who is in the initial. So only you can see 4 is in waiting state, so you cannot put 4. 2 is in initial state, so you can put 2. Okay, so you put 2 inside here. You have put 2. 3 and 4 was already there. You are putting 2. Okay, so once you have put 2 here inside, change its state. So you will change the state of 2 from initial. You will change it to waiting. Clear? And like this you have to continue with all these steps. This thing will continue. You're going to keep doing this now. Okay, so next that you're going to delete is this first element. This is your first element. So you're going to delete tree and visit. When you delete, you put here also when you visit. After visiting, you will find out the neighbors of this. Neighbors of tree. Only tree. What are the neighbors of tree? 4 and 6. Put them here in the adjacent column. Then how will you put them in the queue? Only if they are in the initial state. Among both these vertices, who is there in the initial state? 4 is not in initial state. Who is in the initial state? Only 6. So put 6 in the queue. You put 6 in the queue. 4 and 2 was already there. So you are putting 6. Okay. After you put 6, change the state of that 6 to waiting. Change that state of that 6 to waiting. It is no longer in initial. Because whenever it is in the queue, it has to be in the waiting state. Okay. And like this, you have to continue all the way down till the queue becomes empty. I'm not getting the entire thing, but I hope you are getting it. What? Are you getting it? So now there are 42 students. Can I have an answer from 42 students? Did you all get it? Okay, so please continue like that. Okay, please continue like that. In case you are finding any difficulty, insertion is also in ascending order. Which insertion, Vibhuti? Which step?
So the first step, you insert 1, 3, 4 now. So why it is
Uh,
not 3, 1, 4 like that?
like I think I mentioned. No, you could have put in any order here, Vibhuti. Okay, you could have put in any order. You could have put this as 3, 4, 1. Could have put it in any order. Okay, but just so that we all will get the same answer, and I have just taken this from the textbook. Okay, so in your textbook they have put in the same order. So we'll also continue putting it in ascending order. There's no rule as such. So in a, if you would do it in any other order also, it was fine. You could have put it as 4, 1, 3, any combination that you want. That was fine. Okay, there's no rule for that. But we'll put it in ascending order so that in the end we get the same answer, all of us. Okay. Any other questions before I go to the next method? Confused. Okay, so I'm just warning you before I go to the next method. Okay, so try not to get confused, but you may get little confused. Let me warn you. So I'll go to the next method, that is depth first search. The depth first search also works in the same manner, except that it is having only two states. Okay, so first state is very initial state. And when you pop the vertex from the stack, then we change the state to visited. Okay, so we'll quickly go to this algorithm. Again, it's similar to the previous one. So in case you are not understood the previous one, you can try to understand here again. Except there's one change. Okay, here I'll tell you when we go to the here. Okay, I think I'll show you in the example itself. Here you will get confused. So these are your steps, which are similar to your previous algorithm. Okay, we'll directly go to the algorithm, to the example, and understand this. So this is your example. Okay, I don't know if in that PDF that I shared with you whether this diagram was there. If it's not there, please draw it on your books quickly. Okay, so again, you have to start, choose your starting vertex. So we are taking vertex 0 as our initial vertex. In the exams, you have to mention which is your starting vertex. Okay. Initially, all I in the initial state, so I'll just circle them like this so that you understand better. For exams, you did not circle them, but you could, if you want, you can circle. It's better to understand for you. Otherwise, you will get confused. Okay, so we'll quickly apply this algorithm. Push the starting vertex on the stack, the first step. So we push this starting vertex on the stack. Okay, so this is your stack. Whatever is red in the stack, okay, that will be on top of the stack. Okay, please remember, just to make it easy for you, I made this, whatever is the red value will be on top of the stack. Okay, so when you are studying, you had studied stacks like this, and this was your top of the stack, whatever value was there here. But now the stack is implemented in horizontal fashion in one line. So I hope you understand, it's the same thing, but it's written in one line. So once we have pushed the first element on the stack, second is pop the vertex from the stack. Okay, so only one value is there, so we pop it and visit. So once we pop a value, we visit. So visit means put it in the answer also in the traversal. Okay. Next is find the adjacent values. Okay. So you're going to find unvisited. The important one is unvisited adjacent values. So unvisited adjacent values. So these are your initial state. Suppose it is circle, then it is in initial state. Okay. And if it is visited, then it will be black circle. If it is visited, it will be a black circle. Okay. Means the original diagram it will be black circle means. Just for you to understand. So I find out a vertices adjacent to it. So which are they? There are 2, 1 and 3. Okay, so I write them here. Next, if popped vertex is in initial state, then visit it. Okay, so this one popped vertex was in the initial state. What I do, I visit it. So I rub out this. So when I visit it, I get the neighbors of 0, which are 1 and 3. Okay. And we push all the unvisited vertices onto the stack. So you check this 1 and 3. Okay. Since they are in the initial state, you push them onto the stack. So when you push them onto the stack, first you push this 3. Okay. So like this it would have been. First you would have pushed 3. Then you would have pushed 1. So when you push 1, this is your top of the stack. Therefore, you can see here among both these values, since 1 is the top of the stack, I made 1 as red. Just to help you understand it, 1 is the top of the stack. Okay. Then you're going to pop a vertex from the stack. So which one you're going to pop? 1. Because 1 is the top of the stack. So you pop that vertex and visit. So when you pop 1, you visit. Okay. So like the previous algorithm, whenever you write visit, this 1 has to be written in the traversal. Once you write 1 in the traversal, find out all the unvisited adjacent vertices. Unvisited adjacent vertices. Okay. So now you have popped 1 and visit. So you are going to remove this circle. Because you have visited 1, you remove this circle. So you have removed this red circle from 0 and 1 because you have visited them. Okay. So next you find out the adjacent vertices next to 1 which are unvisited. And whichever are unvisited, you are going to push them onto the stack. Okay. Unvisited vertices adjacent to the popped vertex. So which are the unvisited vertices next to 1? Is 5, 4 and 2. All are unvisited. So you push them onto the stack. So you can see here, these all are pushed onto the stack. So 2 is now your topmost element. Delete it and visit. So when you delete 2 and you visit, you remove the circle from 2. Remove the circle from 2. That means 0, 1 and 2 have been visited. Find out the adjacent vertices to 2. Which are the adjacent vertices to 5 and 3? Okay. Are they unvisited? Yes, they are unvisited. How you come to know? Because they are having a red circle still. Okay. How you know? Because they are having a red circle still. If they were visited, then they would be like this. Black circle, but they are unvisited, therefore they are having a red circle. So you are going to push this onto the stack. Now there is a difference between this here. You can see here 5 when you are pushing is already present. Is already present on the stack, but we push 5 again. Although 5 is already present, 5 is pushed again. So as long as it is unvisited, that is the only criteria we are checking for. We do not care whether 5 is already there on the stack. Okay, since 5 is unvisited, I push 5 again here, second time. I hope you getting this difference from that previous algorithm. Okay, so you will continue like this. I'll trace the entire thing and show you. Okay, so next you're going to pop the topmost element. So now you're going to pop tree. So pop tree and visit. So you're going to write this in the answer here. Also visit means you remove that circle. Remove that circle from tree. Remove that because you have visited. Okay. Find out the adjacent vertices to tree, which is that only one is a 6. So written here 6. Check whether it is unvisited. If it is unvisited, it will have a red circle. So it is unvisited. So you will push 6 onto the stack. So now 6 is your topmost element. So in the next step, pop 6 and visit. So when you say visit, you will write 6 in the answer and you will remove the red circle from 6. So since you are visiting, you remove this. Okay. So all these have been visited now. 0, 1, 2, 3 and 6. You can see here also 0, 1, 2, 3 and 6. They have been visited. So when you visit, you find out the adjacent vertices of 6. Which are adjacent to 6? Only one is there, 9. So write down 9 here. Check whether it is unvisited. Is it unvisited? Yes. So you will push unvisited vertex on the stacks. So you will get here like this. Okay. Next, pop the topmost element. So 9 will be popped. You pop this and visit. So when you visit, write it in the answer and delete this circle since you have visited it. Okay. What are the unvisited vertices adjacent to this 9? Check here. Are there any adjacent vertices? No, there is no arrow from 9 to any of the adjacent vertices. So you leave it blank. Leave it blank. Next, you pop the next topmost element. So after you have deleted 9, who was the topmost? 5. So you delete 5. So you pop 5 and visit. Okay. So write 5 in the answer. Since you are visiting, remove the circle. Okay. Which are the adjacent vertices next to 5? You can check here. Which are the adjacent vertices next to 5? Okay. So when you are checking, see, please check this properly when you are saying. So what you are going to do? Push all unvisited vertices adjacent to the pop vertex. Okay. So when you look next to 5, there are 3 vertices. There are 3 vertices. One is 6, one is 7, one is 8. So you are having actually 6, 7, 8. Let me write it here. 6, 7, 8. Okay. But we can only push unvisited vertices. Okay. Out of these 3 vertices, you can see here, unvisited means they are having a red circle. So who is having a red circle? 7 and 8. 6 is not having a red circle because this is already visited. Therefore, I am writing here only 2 vertices which are adjacent to 5, which are unvisited. Okay. Because here we need to only push the unvisited vertices. So I am not writing this, although it is adjacent. Please note. Okay. Since 6 is adjacent but it is already visited, I do not include it here. I write only the unvisited vertices. Unvisited vertices are 7 and 8. So I push them both and now you get 7 as the top of the stack. Okay. So you delete 7. So when you delete 7 and visit, 7 you write in the answer. Okay. Find out the adjacent vertices next to 7 which are not yet visited. Which are they now? Only one is there, which is 8. So 7 you have visited, so remove this circle. Okay. Okay, 7 you have visited, remove that circle. Only one vertex which is not yet visited is 8. Push 8 on the stack because it is not yet visited. It does not matter that already 8 is there on the stack. Okay, does not matter, like I told you before. So you delete this topmost element and visit. So when you are visiting, write here in the answer and remove this black circle, red circle, sorry, you remove the red circle. Okay, so 1 8 you are deleted, so delete the second 8. So when you pop 8 and you visit, then nothing to visit. Okay, then nothing to visit, you can write here and visit, but the same thing will be written again because you cannot write 8 two times. Okay, you're not going to you're not going to write here and visit because 8 has already been visited. You're not going to visit a vertex two times. You're going to visit a vertex only once. So since you have already visited 8 here in the previous step, here you do not write again visit. Okay, but this answer, if you wanted, you could have written here again. Since you are not visiting any elements, this answer will remain same and nothing here. Okay, so this 8 has gone, so 4 is the top of the stack. So you will pop 4 and visit. When you pop 4, you write 4 in the answer and you are visiting. So visiting means you delete this circle from here. Okay, find out if there are any adjacent vertices which are not yet visited. So you check from 4, there is 7, but 7 is already visited, so you're not going to write here. Delete 5. Okay, you cannot visit 5 again because 5 has already been visited here. Okay, so this answer remains same. So last element is tree. So you pop tree and you cannot again visit tree because tree has already been visited. So this answer remains the same. So in the end, your DFS reversal is this: 0, 1, 2, 3, 6, 9, 5, 7, 8, 4. Okay, and we stop here because your stack has become empty. Did you get this? Did you get it, students? Any doubts about this? You can let me know. You can just look at this slide and let me know if any step you want any explanation. Okay, you need to keep referring to this algorithm as I was telling you about this. Okay, if you are familiar with this algorithm, understanding this becomes easier. So I mean, I hope you have managed to grasp the main idea of what is happening. Take your time now after the lecture is over and solve this slowly, step by step. Okay, slowly, and you should have no problem in understanding this. You keep this algorithm in front of you. Okay, and you start from here, and then you should have no problem. If you are having any questions, we can always take more examples and solve. So right now on this slide, anyone has not understood how we get this DFS? Any questions? Okay. So here's the explanation why in BFS and DFS we have duplicate values. Okay. So the answer is, in DFS, if we are not inserting the duplicate values, then we may not be able to visit the vertices. Okay. So if we don't insert the vertices which are already present in the stack, then we may not be able to get the proper answer. We are not able to visit all the other remaining vertices. Okay. Any questions? Do you want me to explain it again? Let me know.